Greetings everyone. Welcome to my YouTube channel for Kangaroo Maths and Science Academy. I believe you are well and collected. I want to take you through the physical science grade 11 and 12, which is electrostatics, ladies and gentlemen. But this will be part 1, which means I will have to come up with part 2. Right, in part 1, ladies and gentlemen, I want us to talk about Coulomb's law on actually how to calculate the net electrostatic force or on a specific charge due to other charges. Right, let me try to share. Kindly subscribe and also hit the bell button for future videos. Right, and also share the video. Thank you very much. Yeah, let me share the slides. Right, ladies and gentlemen, this is the slide for electrostatics. I believe you will enjoy the session. Right, without wasting time, let me take you through the paper. Okay, just a minute. Right, under this electrostatics, ladies and gentlemen, this is a grade 11 topic actually, but it's also asked also in grade 12. So it means both grade 11 and 12, this is your video is the relevant video for you guys to actually look at. All right, first of all, we have to go through Coulomb's law. This is the learning objective for this session. Then the next session will go through the electric field. We'll be talking about electric field patterns and what is an electric field as a region of space in which an electric charge experiences a force, and also taking you through what is an electric field at a point, which is an electrostatic force per unit positive charge that is placed at that point. But for now, guys, I want to take you through the Coulomb's law. Right, at the end of the session, ladies and gentlemen, you must be able to state Coulomb's law, which states that the magnitude of the electrostatic force exerted by one point charge, which is actually Q1, on another point charge Q2, it is directly proportional to the product of the magnitude of their charges and inversely proportional to the square of the distance between them. So what does this mean? Coulomb's law says that if we compare the force and the charge, the product of the charges, charge 1 and charge 2, there is a direct proportion between the force and the product of the charge, which means that an increase in the charge will result to an increase in the electrostatic force. They are directly proportional, whereas the relation between the force and the square of the distance are inversely proportional. So which means the higher the distance, the smaller the electrostatic force. So they are inversely proportional. So this is according to Coulomb's law. And guys, you need to be able to know this law and also be able to solve questions that are relating to Coulomb's law, which result to the force, the formula which says the net electrostatic force equals to K charge 1 charge 2 over R squared. So this is the formula, the Coulomb's law formula. And it's very important to be able to relate these formulas in terms of the force, the charges, and the square of the distance between those two charges. So it's very important for you to familiarize yourself with the Coulomb's law, whereby we know that the charges are always measured in coulombs. So it's very important for you to be able to know that. Just a minute, guys. I wanted to check something. Right, then, and also you need to also familiarize yourself with, from the formula, then you must be able to know what is the K. K is the Coulomb constant, which is equals to 9 times 10 to the power of 9 Newton meter squared per Coulomb. Newton meter squared per Coulomb. Then again, you must know that the charges, charge 1 and charge 2, these are measured in coulombs. They are measured in coulombs. And remember, in terms of the unit, you can have microcoulomb, we can have I'm saying we can have the I apologize. Yes, we can have the millicoulomb. Yes, we can have the millicoulombs. So the millicoulombs. So we can have also the nanocoulombs, and we can have the microcoulombs. So like if we have these, this is the millicoulomb, which is 10 to the power minus 3. Then if we have this one, this is nanocoulomb, which is 10 to the power minus 6. I'm saying micro, I mean to say. Then we also have this one. This is the nanocoulomb, which is 10 to the power minus 9 coulomb. So this is micro, and this is milli, and this one it's nano 10 to the power minus 9. Then the distance r, this is our distance between the center, and this should be in meters. Then we know the force, it is in Newton. So you need to be able to know how to actually use Coulomb's law in solving problems that are relating to charges. All right. Then again, we are told that we need to be able to solve problems using the equation, just like as I said, using the equation F equals to K charge 1, charge 2, divided by R squared for charges in one dimension. In one dimension, we are referring to those that are actually in a straight line. For example, let's say in some instances you find that let's say you have charge 1 here and we have charge 2. So this is a one-dimensional. Maybe they're at a certain distance apart. So this is an example of one-dimensional. So we can actually add another charge here. So we have charge 1, charge 2, and charge 3, which are at a certain distance between them. So it means we need to be able to solve problems using the equation for charges that are in one dimension, restriction to 3 charges according to your syllabus. So it means in most of the questions will be restricted to only 3 charges, not more than 3. And then again, we need to also be able to solve problems using the equation, the same equation for charges that are in 2 dimension. 2 dimension means we are referring to those that are actually they're at right angle. They're at right angle. For example, if we have, let's say we have, let's say there's a point charge, let's call it point charge A, then point charge B, and point charge C. You see, these are actually 2-dimensional. So this is an example of a 2-dimensional charges. And one other thing you need to also know that since we are dealing with it's an electrostatic force. Remember, electrostatic force, it's a vector, like other kinds of forces that we will learn in Newton's laws, like the frictional force, the force applied, the tensions. These are also vectors. So we know that in terms of vectors, we know it's a physical quantity that must have both magnitude and direction. So this is an example. It means electrostatic forces, it's an example of a vector. It's actually a vector. So now it means here we're going to solve problems using the equation for charges that are in 2 dimensions for 3 charges in a right-angled formation. Like what I said, in a right-angled formation, but limits to charges at the vertices of 3 angled right-angled triangle. And guys, you need to also know that since we are talking about vectors, so it means we need to be able to specify their magnitude and also the direction. So it means it's like we are actually, like when we are dealing with what we call a resultant vector, when we are dealing with a resultant vector, which we will be talking about, like the net force is an example of a resultant vector. So, and what is a resultant vector in grade 11? A resultant vector is just a single vector that is the same effect as all other vectors added together. This is an example, like this is the definition of a resultant vector. However, let's deep dive into the equations. So this is what I wanted to cover today, guys. Then this, like for this part, this will be part 1 session where we talk about Coulomb's law, explain like how to use the formula actually. I don't want to be talking about the principle of charges, the law of charges, and yeah. So for now, I just want to talk about like the calculations of the electrostatic force. Okay, let us go through the equations, guys. Okay, without wasting time, let me take you through the equations. Where we'll be using the formula F equals to K, charge 1, charge 2 over R squared. Then after like the next session, I'll do the electric field at a point. Right, then now here is an example, guys. It says 3-point charges, they lie on a straight line. So we're dealing with one-dimensional charges. 3-point charges that lies on a straight line as shown in the figure. So this is our figure. So we can call this, because yeah, this is our figure. We can call the first charge, we call this charge 1, and we call this charge 2, and we call this charge 3. So we have 3 charges: charge 1, charge 2, or charge 3. Or if you don't want to call it charge 1, charge 2, charge 3, we can also call it charge A, charge B, or charge C. There is no problem. It's like it's our choice here. But for my side, I want to call it charge 1, charge 2, or charge 3. But now I think to make it like simple, like like, yeah, we can call it charge A, charge B, and charge C. Okay, it's fine. Let's do that. Let's call it this charge A, charge B, and charge C. Okay, so we are given 3-point charges that are in a straight line. The question says find the magnitude. You see here they're being specific. They want the magnitude. So it means there's no need to ask to specify the direction. But if they say find the resultant force without talking about whether it's magnitude, so it means here you must also determine the magnitude and the direction. So here it says find the magnitude of the resultant force exerted on the -2 microcoulomb charge in Newton. So it means now here what we're going to do, we have to calculate the net force on charge B, due to other charges, due to charges A and C. So it means here we want to calculate the net electrostatic force on charge B due to charge A and charge C. So now remember, guys, I said a force is actually a vector. And actually, if it's a vector, it means we can represent it as a vector diagram or as a free body diagram. So now, what we're gonna do here, it means we have to say, okay, fine. Because we want to calculate the net electrostatic force or the net the resultant, remember resultant is the same as the net. So the net force or the resultant force exerted on the charge of -2 microcoulomb, which is charge B. So in Newton, which means we want to calculate the net electrostatic force on charge B due to charges A and C. So what we're going to do is we must first, number one, we must first draw a vector diagram or a free body diagram to represent the forces that are actually acting on charge B. So number one, we must draw a free body diagram. We have to draw a free body diagram to represent all the forces acting on charge B. Remember, charge B is our -2 microcoulomb due to other charges. Let me just say due to other charges. So this is due to other charges. So this is the first thing that we need to do here, due to other charges. Here our charges, it will be the A and the C. So number one, we need to draw a free body diagram to represent all the forces that are acting on charge B due to other charges. And how are we going to do that? We know that like charges, number one, the like charges always they repel. There is a repulsion. But unlike charges, this one I believe we learned in grade 10. Unlike charges, they attract. So there is an attraction. So it means this is what we need to actually consider here when we are going to draw a free body diagram. So we're going to say on charge B, remember charge B here, it's the negative microcoulomb. So now, first of all, let's just write all the charges that we have here. Charge A, but it's fine, we can do that after. Now, to take the decision, you're going to say, okay, fine. Let me use a different color so that I can be able to explain this. Ladies and gentlemen, we are interested on knowing the forces that are acting on charge B. Now, on charge B, this is our charge B. Charge B on itself is a negative charge. Whereas charge A is a positive charge. Then charge C also is a positive charge. So what we're going to do here, we're going to compare the type of the forces that are going to occur on charge B due to the other charges. Let's start with charge A. If you look on charge A and charge B, they are at a distance of 2 centimeters apart, which we're going to talk about that later. So since the two charges, charge A and charge B, are actually they are unlike charges, we know that charges that are unlike, they will always attract. So we're going to have an attraction, which means here they will have the same force, but in opposite direction. So this is what we are going to have. So it means here, what we're gonna, like, since we know that we're going to have an attraction because these are the like charges. So it means now, the unlike charges, I mean to say. It means that if we were to draw a free body diagram of charge on charge B, we'll say, okay, fine. On charge B, we are going to have this. This will be the force on charge B due to charge A. So it's a force on charge B due to charge A. So if I write like this, it means this is the force on B due to A. Remember, they will have the same force. And another thing, guys, which we're going to talk about is that when you're drawing this free body diagram, the size of your forces must also tell which one will be higher than the other. And to talk about that, we know that according to this, remember we said Coulomb's law states that the F equals to K, charge 1, charge 2 over R squared. So it means if you want to know like the size of the magnitude, which one will have higher magnitude, it means we look at the distance. Remember we said that the force and the square of the distance are inversely proportional. What does this mean? It means the higher the distance, the smaller the force. They're inversely proportional. So look at the distance between charge A and charge B. It's only 2 centimeters. But the distance between charge B and charge C, it's only 4 centimeters. Which one has a smaller distance? Is the one between charge A and charge B, which means this one will have a higher force because the smaller the distance, the higher the force. So it means this one will have longer magnitude. Like we have to, like it must have a higher force than the other one. So now we have drawn the force on charge B due to A. We know it will move to the left. Then now, since we have compared charge B and with charge A, now we're going to compare charge B with charge C. Right, comparing charge B with charge C, this is what we're going to have. Remember we said the two, okay, these ones, they are unlike charges, they will attract. So they will have an attraction. So they will have something like this. So, but now since we are interested on charge B, so it means we will have this. So it means you're going to have the charge on B due to charge A will move to the left. Already it's an attraction. Then let's compare the one between charge B and C. Charge B and C, since they have opposite sign, so it means they will also attract. So we're going to have something like this. So we'll have an attraction. So it means we're going to have the force on B due to C. So the force on B due to C will be directed to the right. But now, ladies and gentlemen, which one will have a higher magnitude? Obviously, it will be the force on B due to A because it has a smaller distance. So it means on this side, we are going to draw another force that is acting on B, but due to C. But I'm going to draw it as a small magnitude to have a small size as compared to that one. So this is the force on B due to C. And it means this is our free body diagram. We have how many forces? We have 2 forces. This one has higher magnitude as compared to this one because of the distance. You'll see when you're going to do the calculations, you'll see which one has the highest magnitude. Then now, let's take it further. Say, okay, now we want to calculate the net electrostatic force on this charge B. So when we look on charge B, how many forces are actually acting? It's only 2 forces. So because we want the net, remember we talk about the resultant vector as a single vector that has the same effect as all other vectors added together. So it means we are going to combine this, but the combination of these will have a negative effect because these 2 forces are not in the same direction. So one is directed to the right and the other one, it is directed to the left. I believe you guys are following. Because of that, it means we are going to end up subtracting because they're not moving to the same direction. So first of all, we have to calculate the force on B due to A, and also have to calculate the force on B due to C. To do that, we're going to use the Coulomb's law formula, which says the F. Okay, let me use the red color. I apologize, guys. I apologize. Okay. So I'm going to say F equals to K charge 1, like this is our formula, charge 1, charge 2 over R squared. But now, since we are dealing with the force on B due to A, so here we're not going to write charge 1, we're going to say K, can say charge A and charge B all over R squared. This is between A and B. So now, what is our K? We can substitute there, guys. The Coulomb's constant, it's 9. It's 9 times 10 to the power of 9. And what is charge A? Charge A, here we do not put the signs. That we're going to have 5 micro, it's 10 to the power minus 6. Then now another charge B, it's 2 times 10 to the power minus 6. I believe you are following. Divide by the distance between A and B is 2 centimeters, but we need to convert that to meter. So it's 2 divided by 100. So this will give us 0.02 squared. Then now we can calculate the force on B due to A. Then now what will be the answer? So then we're gonna say, okay, fine. We're gonna substitute that. It's 9 exponential 9 multiplied by 5. 5 times 10 to the power minus 6. Multiply again with 2 times 10 to the power minus 6. Then we divide this by 0.02 squared. If I'm not mistaken, let me confirm. 9 times 10 to the power of 9, 5 times 10 to the power minus 6, it's a nano, and 2 times 10 to the power minus 6 again. And this will give us the value of, it will give us the magnitude of 225 Newton. But we can also specify the direction that where is this directed to the left, to the left. I mean, when we are doing the calculations. Then now, all right, then the other one, we're going to say, okay, fine. We have calculated the force on B due to A. Now we have to calculate the force on B due to C. The force on B due to C. Okay? Then now. Okay, guys, just a minute. Just a minute. Okay, guys, let's continue. Right, the continuation that now, Okay, okay, guys, let's continue. I apologize. So let me get rid of this. Okay, I want to get rid of this and mute. Okay, guys. Yeah, I was talking about like how to now we're gonna calculate the force on B due to C. So we're gonna do the same. This will be K charge on B and charge on C over the R squared, which is just the distance between B and C. So we're gonna substitute. This is 9 times 10 to the power of 9. And what's the charge on B? Charge on B, it's 2 times 10 to the power minus 6. What is the charge on C? It's 3 times 10 to the power minus 6. Then divide by the square of the distance. What is the distance between this? It's 4. 4 divided by 100. Then this will give us 0.04 squared. Then let's now calculate the magnitude. So you're going to have 9 exponential 9 multiplied by 2 to the power minus times 10 to the power minus 6 multiplied by 3 times 10 to the power minus 6. Then divide by the square of the distance, which is 0.04 squared. It's very important to confirm before you hit the enter button. So 2 times 10 to the power minus 6, 3 times, okay, everything's fine. Yes, this one will give us 33.75, 33.75 Newton to the right, 33.75 Newton to the right. So we can still confirm. So it's 9 exponential 9 times 10 to the power 9 multiplied by 2 times 10 to the power minus 6 multiplied by 3 times 10 to the power minus 6. So divide this by 0.04 squared. Yes, it's giving us 33.75. But now, since we want to calculate the net electrostatic force, the magnitude actually, so here we want the magnitude, means there's no need for us to specify the direction. So, but now what we're going to do is to calculate the net force on B. So we're going to say, okay, fine. Since we have two, okay, we're going to say the net force on B. So what we're going to do, we're going to say, okay, fine. Since these charges, the force are not directed to the same, they're not moving to the same direction. One is to the right and one to the left. So we can choose, we can say, let's choose right as positive and let's choose left as negative. So it's our choice. You can also choose left as positive or right as negative, depending. But yeah, we can choose right as positive, then left as negative. So now we know, since these are not moving the same direction, we're going to take the one that is moving to the right, so which is FBC, because it's positive, minus the FBA, which is the negative one. So now we are going to end up subtracting because they are not moving to the same direction. So what is the force on B due to C? The force on B due to C, it's 33.75 minus, what is the force on B due to A? 225. So we have the answer there. So it will be 33 minus 225, which will give us minus 191.25 Newton. By the way, the minus is for the direction. And since they said we must not, they want the magnitude. So it means now we're going to say the magnitude here will be 191. Oh, sorry, I apologize. I said the force on BC. So it's supposed to be the F net. So we're supposed to say F net at B. So, okay. So it means now we're going to say the net force on B. So this will be the F net on B. This will be 191.25 Newton. There's no need to specify the direction. But if they said calculate without space, means you have to say the minus is, say it's to the left. You have to say to the left. I mean, if they did not say the magnitude. But since they said the magnitude, it means now we can just say this is our answer. Okay, and remember, it's not about taking right. You can take right as negative, then all same applies. Answer will still be the same. I believe, guys, you are following. I believe you are following. I believe you are following. And this question can change. Sometimes they can say determine the net electrostatic force on A. This time around on A. So it means on A, it means you're gonna look on due to B and also due to C. So it means now the distance between A and B would be 2, but between A and C would be 6. So it will depend with that. Okay, all right. I believe you guys are following. Let us move on to the next one without wasting time. Okay. Okay, just a minute, guys. I want to erase these things. Okay. Remember, practice makes perfect. Okay, then now let's move on. Now we're going to talk about the cases where the charges are now at right angle to each other. They are at right angle. Right. But then now, when dealing with point charges that are right angle, it means somewhere, somehow, you must have a right angle triangle. And also you have to use theorem of Pythagoras because these are at right angle. Unlike the reason of using this is because we are dealing with two-dimensional charges. Okay, here it says 3-point charges A, B, and C of magnitude -2 microcoulomb, 4 microcoulomb, and -2 microcoulomb. So we're given these charges. Let me write them down. Okay, just a minute, guys. So here we have charge A. Charge A, it's -2 times 10 to the power -6 coulomb. And the charge B, it's +4 times 10 to the power -6 coulomb. And charge C is -2 times 10 to the power -6 coulomb. So it's macro. Okay, then now, respectively, are placed in the diagram. You see between charge A and B, these are 10 centimeter. And between this also, it's 10 centimeter. You see now that the distance between A and B and C are the same. But if you look at the charges between A and B, we have 2 and 4. Remember, the product of these 2 and 4 will give us 8. And this one, 2 and 4, will give us 8, which means this will have the same force. They will have the same force. Okay? All right. Then now, the first question says, calculate the net electrostatic force. The net electrostatic force. You see, they did not say magnitude. What they said the net. So it means we have to calculate the magnitude and the direction. So we must get the magnitude and the direction because they did not say calculate the magnitude. They said calculate the net electrostatic force on charge B or on charge B due to charges A and C. Or we want to calculate the net electrostatic force on this. So same applies. Like what I said, we need to also draw a free body diagram. Why a free body diagram? A free body diagram will actually identify or assist us in knowing which forces are actually acting on this charge due to A and B. Then we were going to take that decisions of attraction and repulsion to say, okay, fine. Since now we still have the same, to say, okay, fine, charge A is negative and charge B is positive. What is going to happen? They will have an attraction. They will have an attraction. There will be an attraction force between the A and B. Same force, but in opposite direction. So we're going to have something like this. This is the attraction force. And we're going to have an attraction force. But we are concerned on charge B, not on charge A. So which means if we were to draw a free body diagram on charge B, it will look like this. We'll have the force on B due to A, which is directed to the right. It's to the right, or to the left, I mean to say. This is to the left in terms of direction. So it's to the left. Then now let's also look on the, like we compare the forces between B and C. Still, this one is positive, this one is negative. They will still attract. So we're going to have an attraction, not repulsion, but attraction. This is what we're going to have. So it means now we're going to say, okay, since you're concerned on B, we're going to have, they will have the same magnitude, guys. We're going to have the force on B due to C. And this one is directed downwards. Is directed downwards. Now, look at this. The directions are no longer, here, this one is the horizontal part and this one is the vertical. Remember, you cannot combine left and down and calculate the resultant with that. So it means now this becomes a two-dimensional shape. I'm saying we are doing with two-dimensional charges. So which means that here, we have to come up with what we need to construct a right-angled triangle so that we can be able to calculate the net electrostatic force B due to A and C. All right, and to do that, we're going to use the principle of tail-to-head method. Tail-to-head method. If you are not using tail-to-head method, we can use parallelogram approach, where you have to use tail-to-tail. Parallelogram. Okay, one of these, either tail-to-head or tail-to-tail, and to construct this. But before we start with this, let's now calculate the force on B due to A. I think we dealt with this. This is K, charge on A, charge on B, divide by the square of the distance between A and B. Let's do the substitution. Ladies and gentlemen, so it's 9 times 10 to the power of 9 multiplied by, okay, let me put this in brackets. What is the charge on A? Charge on A is 2. We don't use the minus there, sometimes 10 to the power minus 6. And what is the charge on B? The B, it's 4. 4 times 10 to the power minus 6. Coulomb, divide by the square, the distance between A and B, it's actually 10. So we're going to say 10 divided by 100, 10 centimeter, I need to say. So this gives us 0.1 squared. Okay, then now let's calculate the force. It's 9 exponential 9 multiplied by 2 to the power, like 9 times 10 to the power of 9 times 2 times 10 to the power minus 6 times 4, 4 times 10 to the power minus 6 also, then divide by 0.1 squared. And this one will give us a magnitude of 7.2 Newton, 7.2 Newton. So we can say to the left. To the left. Then obvious, there is no need for us to calculate this because they will have the same magnitude. So this will be still 7.2 Newton, but this will be downwards. I believe you understand why, because the force, like the charges are the same. If you substitute charges B with 4, 2, then it will still give us the same answer. So with the same distance. So it's just a waste of time to calculate that. All right, then now we are going to construct our right angle triangle. So I want us to use tail to head method, guys. I think it's still straightforward. Let's use the tail to head method. You can also use tail to tail. There is no problem. Okay, let's use tail to tail method to construct our right angle triangle. So how are we going to do that? Well, what we can do, guys, let's just construct a Cartesian plane. I think it's easier with the Cartesian plane. Let's construct the Cartesian plane. Okay, can I drag this down? Okay, fine, let me just leave. I wanted to drag it somewhere. Yeah, okay, fine. It's easier this way. We'll come back to that because already we want this. This is what we want, okay. Let me try to erase this because already we spoke about this now. Distance is the same, right? 10, 10. Okay, I want to be sure, guys. I want to be sure. Okay. Okay, then now okay, now let's do this. Let's construct, let me use a different colors so that everyone can understand. Okay, let's say we have okay, it's fine. Let me just use both. I'm gonna draw a Cartesian plane here. Let's construct a Cartesian plane. I apologize, guys. It's easier to explain it using Cartesian plane so that everyone can understand. This is the X, this is the Y. Okay, let's do this. Let's say this is the point. This is our point, is our free point diagram way here. So what I'm going to do is I'm going to use tail to head method. And with tail to head method means, okay, if this is the origin, let's start with the horizontal part, the one moving horizontally, which is the one to the left. So it means we're going to have this. I apologize, guys. So we're going to have, from this, we're going to have this, the force on B due to A. Remember, I'm using tail to head, so it means with the tail, it's the tail, and the head. On the head, I have to put a tail. So now, what is the next force? The next force is the one that is moving downwards. I believe you guys are following. Okay, let me use this. Okay. So you see, I've started with the one left tail to head. Then here I have to put another tail, then a head. Then we're going to have this. So now this is the force on B to C, which is downwards to the left. Remember, it's tail to head. So it means we're going to have an angle of 90 degrees. And now in that case, then I'm going to do away with the, remember, we can also start with this, with the down. So we say tail to head, then to the left is still gonna, so we'll end up having parallelogram. It's still fine. What I'm gonna do for now, let me do away with the Cartesian because I wanted to explain how to actually construct it. Okay, now we have everything. Then now I have to draw a resultant. And how do we see that we have a resultant? Remember, I explained it last to say, where there is a resultant, you'll see by it must have two heads on it, two tails, or two tail and two heads, two tail and two heads. So we must have two tails. Remember, this is a tail. to tail, and to head. So it means this is our resultant here. From here, this is our resultant. So it has to tail and to head. So this is our F net at B. And now, since this is our F net at B, how are we going to represent the angle? Remember, look, this is the direction of the force. Né? So it means the direction here, we're going to say from the x-axis, we draw the angle. So this is our angle here. So this angle here, because this is at right angle, it is the one that represents the direction. So we have to calculate the direction by looking at the angle from the x-axis up until we get our resultant. So that's the angle. So it means now, since we have this, then we're going to use theorem of Pythagoras. We know that theorem of Pythagoras says the square of the hypotenuse equals to the sum of the square of the adjacent and the opposite. So what we're going to do here, we're going to say, okay, fine. We have everything. What is the R? The R is the F net at B squared. The X, we can take it as the force on B due to A, so which is just 7.2 squared. Then the other one is 7.2 squared. Then it will give us the F net at B. Then we're going to work this out. So it's 7.2 squared plus 7.2 squared. This will give us 103.68. And to calculate the F and the net force at B, we have to put the square root, the root sign. So the square root of an answer, so this gives us 10.18 Newton. By the way, this is the magnitude. This is the magnitude. And here the question wants the magnitude and the direction, because they said calculate the net electrostatic force on charge B due to other charges. And how to calculate the direction? Always, guys, when you're calculating direction here, you have to use tan, because this is our angle of interest. And to calculate that, what we're going to do, let me try to use a different color. We're going to say, okay, fine. The angle of interest that we're looking for is this one. This is the one that represents the direction. So we're going to say, to calculate that, we look at the angle. The angle, this is the opposite. This one is the adjacent. Usually we use tan, but you can also use other ratio, but it's easier when you're using tan. So you can say tan of theta, it's opposite over adjacent. Okay, let me use like a visible color. I feel like this one it's not showing well. Okay, let me just use the one we're using. Okay, so this is, we're gonna say the tan of theta, it's opposite over adjacent. And guys, what is the opposite here? The opposite, it will be the force of BC due to force on B due to C, and the adjacent will be the force on B due to A. And since these have the same magnitude, so it means our angle will just be 45 degrees, but let's just show. Because we're going to say tan theta, this is 1, so theta will be the second function, tan of 1, so the answer becomes 45 degrees. 45 degrees. Okay, 45 degrees. But also, if we were to draw a compass, by the way, this is this east or west? Okay, let's just leave it because I think it's west. So is it west compass direction? It's north, south, east, and west. Okay, so this will be west. And if it's west, it means if we draw the compass, this will be south. So it means this is just between southwest actually. Yeah. Okay. So this is what you need to know. Actually, when you're dealing with charges that are at right angle, if they say calculate the net, then you have to use the theorem of Pythagoras and also to calculate the angle for the direction. I believe, guys, you're following. So again, you can pause the video, guys. You can pause the video and go through this question on your own. Okay, let me erase this. This is your activity. I've just left it as an activity just to go through it on your own. Try to check if you guys are following. And if you are not following, then kindly keep in touch with me. I'll be happy to assist you, ladies and gentlemen, wherever you don't understand. Okay, remember, practice makes perfect. So we will proceed with the next session, which is for part 2 for electrostatics, where I'll be talking about the electric fields and how to calculate the electric field at a point. Yeah, and guys, also we'll also address the cases where you find that you have like charges that are actually hanging. But this one is particularly for both grade 11 and 12. For example, let's say they say there is like a charge here, and this charge is actually hanging from a wall, which is at an angle of, let's say, 8 degrees. It's just an example. Then there's another point charges here, maybe with a, then they're at a distance of, let's say, R. Then they give you charge 1 and charge 2. Then they ask you questions. Maybe you have to draw a free body diagram. Yeah, we'll talk about this in the next video. Yeah, guys, let me pause here. Kindly like the video, subscribe, share with your friends, and that will be much appreciated. Thank you, guys, for your time. Take care. Bye-bye.